A ship can be climbing normal storm waves one after another, and then the ocean in front of it can rise into a wall twice as tall as everything around it. Not a tsunami, not a legend, a rogue wave. The strange part is not just the height. It is the way it can appear like the sea has made one wave out of many, with a deep pit in front of it, a steep face above it, and sometimes a direction that does not match the storm at all. For a long time, waves like this sounded like sailor exaggeration because open ocean storms already look huge. But rogue waves are not just big waves. They are extreme storm waves that are unusually large compared with the sea around them. If the surrounding significant wave height is about 30 feet, a rogue wave can be more than 60 feet from trough to crest. In the worst moments, that is not a rolling hill. That is a moving cliff. To understand how the ocean does this, start with a simpler question. What are you actually looking at when you see a wave? It feels like a pile of water racing across the surface, but most of the water is not traveling all the way with the wave. The wave is energy moving through water. Water near the surface rises, circles, and falls as the energy passes through. So the ocean is not only a surface, it is a giant moving field of energy, with different wave patterns crossing, stretching, speeding up, slowing down, and sometimes stacking at exactly the wrong moment. A storm does not make one perfect line of waves, it makes a crowd. Some waves are short and choppy, some are long swells that have traveled from far away. Some are being pushed by the current wind, others were born under a different storm system days earlier. Out on the open ocean, all of those wave trains can meet in the same patch of water. Usually the meeting is messy but harmless. One crest lifts another a little. One trough cancels part of a crest. The surface keeps rearranging itself. But sometimes the timing becomes brutally perfect. Imagine several wave crests arriving at the same point at the same time. Each one adds its height to the others. That is constructive interference. It is the same basic reason two ripples in a pond can merge into a larger ripple, except on the ocean, the ripples can already be the size of buildings. For a few seconds, the sea borrows energy from the surrounding wave pattern and concentrates it into one extreme peak. Then the pattern falls apart again. The monster does not need to last long. It only needs to exist when a ship is in its path. This is why rogue waves feel like an ambush. The captain may be reading the sea correctly, the vessel may be handling the storm, the waves may be large but consistent. Then one wave rises out of the pattern because several pieces of the pattern briefly arrive in phase. The wave seems to come from nowhere, but it did come from somewhere. It came from the hidden arithmetic of moving water. The scarier part is the trough. A rogue wave is measured from trough to crest, and the trough in front can be unusually deep. So before the wall appears, the ship may drop into a hollow. From the deck, the horizon can vanish. The bow points down. Water towers ahead. The wave is not just tall, it is steep. Many normal ocean waves have long slopes. A ship can climb them because the water rises gradually. A rogue wave can have a short, sharp face, with too much height packed into too little distance. That steepness is what turns a wave into a battering ram. A vessel designed to survive heavy seas expects loads spread over time. A steep wall of green water hits differently. It can smash windows far above the waterline, flood decks, rip gear loose, and twist steel in ways that ordinary rolling waves may not. The ocean has another trick that can make the stacking worse. Currents can focus wave energy like an invisible lens. Picture waves traveling one way while a powerful ocean current moves against them. The waves run into flowing water. Their forward motion slows, their spacing can shorten. The energy that was spread across a longer distance gets squeezed. The faces steepen, the waves bunch up. In places where strong currents meet storm waves, the odds of extreme waves can rise. This is one reason regions near major currents have such dangerous reputations. The Gulf Stream can push fast water through the North Atlantic. The Agulhas Current runs along the southeast coast of Africa. When large storm waves oppose currents like these, the sea surface can become a trap where energy piles into sharper, higher waves. The current does not need to build the whole wave by itself. It only needs to arrange the ocean so an already violent sea can focus its violence into one place. This is also why a rogue wave can arrive from an unexpected direction. The wind may be blowing from one direction, but the ocean remembers older storms. Long swell can travel across entire ocean basins. Currents can bend wave paths. Coastlines and underwater features can redirect energy. Two or more wave systems can cross at angles, making a confused sea with peaks that do not line up with the local wind. In that kind of water, a ship may be facing the main waves only to have an extreme wave form at an angle. From the bridge, the ocean stops behaving like a single moving road and starts behaving like intersecting traffic. The dangerous wave is not always the one in the lane directly ahead. A crossing sea can make the surface look like a grid of moving ridges. Where ridges intersect, a peak can jump higher. The result may look less like a smooth wall and more like a jagged, mountainous lump with a breaking crest. Mariners sometimes describe holes in the sea, then a wall, then white water exploding over the top. That description sounds dramatic because the physics is dramatic. Waves are not solid objects, but they can briefly create shapes that act solid enough to break ships. The proof that these waves were real came in one of the cleanest ways possible. On January 1, 1995, an instrument on the Draupner gas platform in the North Sea recorded a wave about 25.6 meters high, roughly 84 feet. The surrounding sea was already rough, but this wave was far larger than the waves around it. It was not a blurry story told after a disaster. It was a measurement. A laser had watched the ocean's surface rise and fall, and the numbers showed a wave that should not be dismissed as folklore. After that, rogue waves moved from sea stories into hard ocean science. The Draupner wave did not mean every old monster wave story was true exactly as told. It meant the ocean really could make waves much larger than the surrounding sea state, and it could do it in deep water, away from shore, without an earthquake, without a landslide, and without a tsunami. That difference matters. A tsunami is usually a long wave generated by a huge displacement of water, often from an undersea earthquake. In deep ocean, a tsunami may pass under a ship as a broad rise that is not dramatic at the surface. A rogue wave is different. It is a surface gravity wave born from wind waves, swell, currents, and wave interactions. It is shorter, steeper, and far more like a sudden impact. A tsunami becomes terrifying when it reaches shallow coastlines. A rogue wave is terrifying in the open ocean, where people used to think the biggest danger was simply the storm itself. The name rogue makes it sound like the wave has broken the rules, but it is really following rules that are hard to see from a deck. Wave height at sea is statistical. When a forecast says a certain wave height, it usually does not mean every wave will be that high. Significant wave height is based on the average height of the highest third of waves. Many waves will be smaller, some will be larger. In a chaotic storm, rare extremes are expected. A rogue wave is the extreme tail of that pattern, pushed higher by focusing, crossing seas, currents, and sometimes non-linear effects where energy shifts between waves in a group. In plain language, the sea can organize its chaos for one devastating instant. Think of a crowd clapping randomly. Most of the time, the sound is scattered. But if enough hands clap together at the same moment, the room cracks with one sharp sound. The ocean can do something similar with crests. The energy was already there, spread out in the storm. The rogue wave is the moment that energy lines up. That is why the wave can vanish almost as mysteriously as it appeared. Behind it, the sea may go back to being just a very rough sea. The monster was real, but temporary. For ships, that temporary shape is enough. A large vessel is strongest when it can meet waves bow on and climb them. But if a rogue wave comes steeply or from the side or breaks over the bow faster than the ship can rise, the forces can be enormous. Water is heavy. 1 cubic meter weighs about a metric ton. When a breaking crest throws thousands of tons of water onto a deck, the impact is not like spray, it is moving mass. Windows that seem safely above the ocean can suddenly be underwater. A deck that was in the air can be buried. The ship is not fighting a wave in the poetic sense. It is being hit by a temporary wall made of weight, speed, and gravity. The most unsettling thing about rogue waves is that they are not supernatural interruptions in nature. They are nature being ordinary in too many ways at once. Ordinary wind makes waves. Ordinary storms send swells across the sea. Ordinary currents bend and squeeze them. Ordinary interference stacks crests. But when all those ordinary processes meet in the wrong place, the result looks impossible. A flat horizon becomes a cliff. A moving surface becomes a falling wall. A storm that was dangerous becomes, for a few seconds, something much worse. So the old image of a lone ship facing a sudden wall of water is not just a dramatic painting. It is a real ocean moment. The wall does not come from nowhere. It comes from everywhere around it. From wave trains crossing, from currents pushing back, from crests arriving together, from troughs dropping away, from the hidden pattern under a chaotic sea. A rogue wave is the ocean briefly solving itself into one terrible answer, then erasing the evidence in foam.